Hi, my name is Esquinazi, and I will explain you shortly the main aims and result of this work. In this figure, you see the normalized electrical resistance as a function of temperature for a bulk graphite sample. For years, we all believed that the metallic-like behavior, as well as the lower the absolute resistivity of the graphite sample, the more ideal is the sample. Well, you can see in these two figures that these assumptions were not really correct. At the left, you see the increase in the absolute value of the resistivity, decreasing the thickness of the graphite sample. And on the right picture, you see the change of the temperature-dependent decrease in thickness. Below a thickness of the order of 100 nanometer, the temperature dependence appears to be semiconducting-like. So, neither the absolute value nor the temperature dependence of the electrical resistivity of bulk graphite samples appears to be intrinsic. The reason for that is the influence of lattice defects, in particular of well-defined internal interfaces in the sample, as we can see in the next picture. Here you see a TEM picture of a graphite lamella with the electron being applied parallel to the graphene planes of the sample. The region of different gray colors means single crystalline graphite region with a slightly different orientation between each other. The key point here is the existence of well-defined two-dimensional interfaces between those regions. Taking into account this internal structure, we take a simple parallel resistor model and assume that the metallic-like behavior of the resistance is mainly due to the interfaces, and the single crystalline region are semiconducting. The prefactors are free parameters necessary to fit the resistance of different samples with different thickness, e.g. is the band gap. It is clear that the larger the thickness of the sample, the larger will be the interface contribution. In other words, graphite sample without interfaces should not show a metallic behavior. Unusual is, however, here the thermal activated function assumed for the interface contribution. A possible reason for this will be given at the end. You see here again the normalized resistance as a function of temperature of a bulk graphite sample. The red line is a fit, assuming only the interface contribution. In other words, the contribution short-circuits the graphene layers. Decreasing now the thickness, you see different behaviors, which can be very well fitted, changing the relative contributions. For the CNET samples, mostly a semiconducting behavior is measured. The saturation at low temperatures is due to the always present free sample surface or phase with the substrate. Important to note is that in all fits we use similar bandgap values supporting the assumption of the semiconductivity of the graphene layers within the single crystalline region of the graphite sample. Concluding, ideal graphite appears to be a narrow gap semiconductor with an energy gap of the order of 40 mV. The resistance is given by the parallel contribution of graphene layers and interfaces, including the surfaces. Clearly, for samples with no or not well-defined interfaces between crystalline regions, we expect no metallic-like behavior, just because this is not intrinsic of ideal Bernal graphite. An important hint and future tasks are related to the thermal activated behavior from the contribution of the interfaces. This suggests the existence of granular superconductivity within the interfaces and can be understood in principle on the basis of this model. The corresponding citation as well as further experimental evidence for this interpretation can be taken from the manuscript. We thank you for your attention.